important that you're working through the problems because they will be reflective of the exam. Okay, so we talked about J coupling last time, and what we ended on was what happens when you have two different spin systems that are coupling. Oh, that's a pain. There we go. The right angle. And so we talked about the n+1 rule that works when we have J values that are equivalent. And so we saw that with, for example, if you have a CH2 that's non-diastereotopic to a CH3, if you have this type of spin system, what we end up with is seeing this observed as a quartet as the result of the influence of the methyl system, and so we would expect a peak shape that way. And the reciprocal is that this would show up as a triplet because those the two methylenes are equivalent, and that's as the result of the fact that this one's little magnetic spin is affecting this one's larger one, and vice versa, and they're affecting each other in equivalent ways. Now, what we ended on when we started to consider these types of systems is that if we had something, for example, if we had some lack of symmetry in the molecule, so for example, if we had diastereotopic methylenes that were coupling to one another, and we had a methine, and this methine is seeing these two, that it could see them in different ways. And this is essentially a pattern that we can tend to look for. And remember that these are reciprocal values because the influence of one nuclei on the other is reciprocated back and forth. And so what does this look like? Well, you can't just apply the n+1 rule in that case. In this case, what we say is that we treat these spin systems differently like we do with respect to their chemical shift. And so this one is going to split it into a doublet, and this one's going to split it into a doublet. And that's what we're going to observe. Additionally, there's additional coupling that's between these two. And that means that we're going to have, as well as that, we're going to have this geminal coupling. And so I'm not going to go through the huge detail of what these things look like, but for our treatment as well, with respect to what we're looking at now, I'm just accounting for these non-simple spin systems that you might see in some of the problems. But before I go into some of that detail, I just want to show you what kind of messes with spin systems so that we don't get something that looks like the n+1, the Pascal's triangle simple splitting. Okay. So spins, coupling is different in terms of magnitude as the result of a variety of different things. The common one that we're dealing with, or that we've talked about in terms of this scalar coupling, is what we call a 3-bond coupling. So this is 1, 2, 3. We're dealing with the two protons that are interacting with each other, and this is called a J3 coupling. Okay. And what affects the J3 coupling, there's a few things, but the main thing that affects the J3 coupling is the angle around the bond. So in flexible systems, that angle is averaging itself over a range of times, and we'll talk about that type of coupling in a second. But in rigid systems, this actually matters. And so there's this way that we predict the magnitude of a J3 coupling, and that's the Karplus equation. And if we plot the Karplus equation, it has bond angle on this side, on the x-axis, and it has J in hertz on this. And what is known about the Karplus equation is that, okay, so this is 90 degrees. It's a cosine relationship. This is 0 degrees, and this is 180 degrees. What we know about the Karplus equation is that it it's at its minimum at 90 degrees, and its maximum, it's kind of a distorted cosine function. It's at its maximum at 180. And so this range that we tend to see, this is about 10 hertz right here. This is 15 or so. And, these are ranges that way. And this is 1 to 2 hertz. And so the bond angle, what that influences is how strongly those spins are interacting. Remember what we talked about last time. If one spin is interacting stronger than the other one, then we have inequivalent J's, and that's what leads to some complex coupling. But you can imagine this as two wires that are, two nuclei that are communicating with each other magnetically. That's what leads to the triplets and the quartets and everything. But that's different based upon this the bond angle. And so in a rigid system, what we'll see is that these values differ depending on the relative bond angle. And where we really tend to see it is, for example, in double bonds, we can tell things like, is it a cis relationship or a trans relationship of a disubstituted double bond? Remember, these are two different stereoisomers, because the J value here is going to be around 15 hertz, and the J value here is going to be about 10. Well, what's important to note in these cases is that it does tell us a little bit about the system, and if we look at something like our classic ethyl group, this type of spin system, we tend to see this J value between these two around 6 to 8 hertz. And that's because we're dealing with the chemical average in that case of all of the geometries that cycle through somewhere between 0, 180, and 90 as a result of this spinning faster on the NMR timescale than what we see. And so that's why it averages to about 6 or 8 hertz in these very flexible systems. And only when we get some rigidity do we start to see this happen. The other place that we can see things that are rigid and that have importance that way is if we have two axial protons next to each other on those adjacent, that bond angle is 180. That dihedral bond angle is 180, and so as the result, we have a J value that's greater than 10 hertz in that case. And the equatorial, they're smaller because you're closer to 90 degrees. It follows that type of rhythm and pattern. So these are what we call vicinal vicinal J's, and these are by far the most common ones that we use to predict. It's what we use in the N+1 rule frequently, but that's the one that we tend to predict. Now there's a few other cases that I want to describe to you before we move on. If we have a case where we have inequivalent CH2s, okay, so these are diastereotopic methylenes. Remember that word. These are diastereotopic to one another. There is a J2, and so these guys are through two bond coupling, and that's what we call a J2, and it's also called geminal, meaning they're on the same carbon atom. And that J value, it's approximately 10 to 15 hertz, although it can go up to 21, which is a big coupling constant value. And so it makes sense that it's a large coupling constant because they're only two bonds away from one another, and therefore they're very strongly coupled to one another, and as a result, we see a large J value. One nuclei is in strong communication with the other as the result of that J. So that's a common one. Now, another common one that we'll deal with that way is long range coupling. And why I'm explaining all these in just an overview sense is it's because it's things that we see in a proton that do confuse students. And, again, this course is presenting data. And in data, sometimes we see things, sometimes we don't. but I want you to be prepared once you see it so you don't freak out. All right. So long-range coupling can happen where we tend to see it is in a couple of different systems. The most common one is when we have a aromatic ring because of the extended pi system, we not only see a coupling pattern between adjacent hydrogen atoms, and so we have our vicinal, we call that a para coupling, but also what you see because of the extended pi system is a coupling that's a meta coupling. And so those two, of course, are possible and probable, and so we tend to see them in these systems. Oh, sorry. Yeah, thank you. I was going to say that we don't typically see ortho, but as man, I'm doing it again. We don't typically see para. How did I mess that up? Yeah. So the ortho ones next to each other, which are closer in proximity, or the J3 is different than this 4-bond coupling that we would see in these cases. As a result, which one do we think is going to be a larger coupling given what we know about the nature of coupling? Ortho, yeah. Ortho is typically 7 to 10 hertz in terms of its value, and that's a constant, versus a meta, which can be 1 to 4 hertz. And so we see this fact that distance does matter. Para, sometimes you can see it can be a half hertz to 1 hertz, but we see that tapering as the effective distance from one another. Okay, so that's an important one. Another important one that we see, or that we can tend to see, is allylic coupling. And so this is a 4-bond coupling phenomenon. So 1, 2, 3, 4. And this communication can happen as the result of the fact that you have a pi system that is essentially transmitting the spin information between the two. When we have pi systems, they're better conductors, essentially, in NMR. That is what leads to those two protons that, despite them being far away, communicate with one another. And this kind of J-allylic coupling is one that we tend to see. And you can see benzylic too. It's analogous. And that can be 1 to 4 hertz as well. It's small. It works in propyogenic systems where we have hydrogen on this, and this is one that's part of your problem set. But again, we can get a small coupling constant that's between these two. Okay, and so these are other things that contribute that way to that coupling picture. Now, there's one other kind of special case that I do want to describe, and that's again when we're dealing with long-range coupling. There are weird cases in rigid systems, and I think we might not see this quite yet. There might be some problems that we deal with that we see this. When you have an aliphatic system, we don't typically see a long-range coupling when we have just sp3 hybridized carbon. But when they're very rigid and restricted in rotation to one another, what it does is it kind of completes the communication by developing what we call a W coupling, which is a 4-bond coupling, right? 1, 2, 3, 4. It's a J4, and that ranges 1 to 3 hertz, okay? And those are smaller coupling constants, but it's the result of this kind of rigid system. And so when we start to solve structures that are like terpenes and those types of molecules, there's a lot of these bicyclic architectures that lend themselves to this W coupling. And I hope that you can obviously see why it's called a W coupling in this case, because if the protons enter a conformation that look like a W or an M, I typically draw it like a W, then that's you tend to see that long-range coupling. So what's important in these cases is that we can have different magnitudes of coupling, and as a result, you can have communication between nuclei that are different as the result of their relationship. And so what ends up complicating NMR spectra, and I'm not expecting you to be able to assign things yet in terms of coupling constants, what complicates NMR spectra is that if we were to go through and ask, well, how about in this case, what are going to be the patterns of these groups? And so if I were to just go X, Y, Z to break symmetry, we know that we would have 3 different proton resonances. Therefore, those 3 are chemically distinct. They're going to communicate with each other because of what I just described to you. And if we were to go from, for example, what this proton is going to look like, how many partners is it being affected by? 2, right? And so if the magnitude of the coupling constant, if they were both ortho, what would it look like? If the magnitude of the coupling constant to the 2 partners was the same, if they're communicating the same way, we would use the n+1 rule. It would be a triplet. But they're not, right? Because the relationship of it to this proton is different than the relationship to this proton by meta. And so what we would actually see in this case is a doublet of doublets. And the small coupling would be the meta one, and the larger coupling would be the ortho one that we see in that case. And we can go through all of these that way. For example, if we look at this guy, right, its relationship with this one is ortho. We might actually see a triplet in this case because the green and the red magnitudes of coupling are about the same to one another, and so that might apply the n+1 rule, or it might look that way. And so if we have the green peak, we might see something that looks like a triplet that way. And then, this yellow proton, that one's going to look much like the doublet of doublets because, again, these are dramatically different than one another. And so that kind of complicates things in that way, and that's because we have chemically inequivalent nuclei that are communicating with each other in different strengths through the spin system. Okay. So I hope that you guys have looked at the problem set because there's this case too. So if we have a stereocenter, for example, in a molecule, and we have diastereotopic methylenes, it's complicated, much more of a complicated picture because instead of, for example, if we just look at this proton, instead of that proton just being split as a triplet, like we would expect in a simple coupling pattern, its communication to these 2 different chemically unique protons is different than one another. Okay, and as a result, it is seeing those protons differently. And so instead of it being a straight triplet, I would say that if we took this yellow proton, again, we're going to have a case where we have a doublet of doublets. It's going to kind of look like this. And then remember, we also have, in this case, geminal ones. And so if we were to just take one of these guys, and I guess I'll highlight it blue. So if we were to take one of those and look at what it looks like, the other peaks are going to look much different than what we're usually expecting. We're going to see, 2 doublet of doublets because they're coupled to themselves. And actually, they're going to lean toward one another, and we'll get into that in the second half of this class. But you would expect a pattern like this. What that tends to look like is, all I'm trying to describe here is that these protons are going to look like that. This proton, of course, is going to look like this. And that's because they're coupling to each other in different magnitudes and they're coupling to themselves. And when we increase chemical inequivalence, we increase the complexity of the coupling. And so you can look out for it, and we're going to go through a couple examples in about 5 minutes. We'll go through a couple of examples that way, but you can point out that, okay, that should be a triplet, but it looks a lot more complicated, and that's because of these lack of symmetry, the difference in coupling constants. The more chemical inequivalence we have, the more different types of protons, and the more that they're communicating, the more complicated the coupling picture looks. Does everybody understand that? Everybody get what I'm saying? Yeah. So if you have many things that are communicating that are different than one another, the signal is going to be split more in the chemical field. As a result, it's going to look a lot more complicated. What's really neat about this is once you can solve some of these complicated coupling patterns, you can actually solve stereochemistry of your molecules. And that's the next half of this course is one of the skill sets that we'll learn. Okay. There's another thing that complicates NMR spectra, and it happens because of symmetry. Okay. So if we have dichlorobenzene, benzene for example, how many different NMR signals? 1,2-dichlorobenzene. 2, right? Because we have a plane of symmetry here, and we have this one, right? And this one, right? And so we would expect maybe, this guy might be a doublet, and this one might be a triplet. We could deal with that, or it's going to be a doublet of doublets. And actually what you end up seeing is a mess. You get 2 signals that are a mess. And they look really weird, and we'll see what they look like. And, one of them is downfield than the other one because of its location. But the coupling pattern looks a lot more complicated for each of them than what you would expect. And here's the issue. You can be chemically equivalent, but magnetically inequivalent. And here's the reason why. So the relationship of this blue one to that green one is the same, right? But what about the relationship of this blue one to that green one? Versus this blue one to this one versus this one to that one. They're different, right? Because we know that this blue one, if we call this, let's call this the A system. Let's call this the B system, right? A and B have a different relationship to their green proton, even though they're coupled to chemically equivalent protons. It's a weird phenomenon called magnetic inequivalence. There's a bunch of examples in our book. The best analogy I can give is if you had 2 sets of identical twins marrying 2 sets of identical twins. Their relationship through marriage is the same, but the relationships between the in-laws is different as the result of, but even though they're genetically identical to one another. And so this magnetic inequivalence is something that I just want you to be on the lookout for because it complicates NMR spectra, and it could complicate your analysis that way. Does anyone have it? So twins marrying twins, where the relationship between the A pair and the B pair are the same, but the relationship between the 2 set of pairs is different. Okay. All right. There's one more phenomenon to talk about with respect to NMR before we can take a look at spectra, and that is exchange. All right. So if we deal with things like NH or OHs and these types of protons, we know that those types of protons should show up, and they should show up in an NMR spectrum. Except the problem is that often we're using deuterated solvents such as methanol, or we might add D2O to a spectrum where we might be able to identify it. And what we tend to see in that case is that over time, these types of protons will exchange with deuterium or exchange with each other. And as a result, they'll become NMR non-detectable. And so usually exchangeable protons, because of hydrogen bonding and this exchange happening slower than the NMR picture, will end up looking like very broad peaks. So you'll get a broadness. Sometimes those peaks can be so broad that they're just in the noise someplace, or sometimes we don't see them at all. And so the overall aspect is that it's exchangeable protons can be um, undetectable. And part of this issue is that we also don't tend to see, even though it's not impossible to see, we don't see coupling through exchangeable types of protons. So an OH doesn't tend to couple to adjacent CH, even though you can see that sometimes. In NMR phenomenon, the exchange prevents that strong communication, and we don't tend to see that coupling. All right, and that goes for carboxylic acids. It goes for pretty much anything. There's a whole chapter about exchange on the book, and you could take a look. But overall, we might not see the OHs. Okay, so that finishes up our summary of proton NMR. And now we're going to turn over to the problem set, and we'll go through a couple of the cases. The point of this problem set